Welcome back. So what was I saying? So yeah, so we can attack this with the same procedure as up here. So let u equal secant. That means dx is going to equal all that junk. So let's see what happens to our actual integral. So we have tan cubed of x, and then instead of dx, I'm going to write all of this. Like so. Alright, so one of the tangents gets cancelled, and also secant is the same as u, so we may as well write that. So we have tan square over u du left over. Now, we want to get rid of this x so that we have nothing but u's left over. So we use this formula. So tan square becomes secant square minus 1. And now, of course, we're in a better position because secant is the same as u. So we get u square minus 1 over u du. Now, when you have multiple terms on the top and only one term on the bottom, you can just divide both of those terms. So this is the same as u squared over u, which is u, minus 1 over u du. And now this is easy enough to anti-differentiate. So u, well, we can hit that with the power rule to become u squared over 2. And then the antiderivative of 1 over u is natural log. Natural log of absolute value. So the last thing to do is to replace u with secant. Like so. And there we go. So yeah, even though there was no secant present here, this same strategy still worked. And yeah, it could be tangent to any odd power, and this would still work. This strategy here. Actually, does it even need to be odd? Because no, yeah, it does need to be odd. It needs to be odd because after having one of them cancel out, we need the power here to be even. Because if the power here is even, then we can use this formula. Yeah, so the power does still have to be odd. So that's it for this one. I suppose one thing that you could do, though, just in case the answer in the multiple choice isn't matching up, is notice secant is the same as 1 over cosine. So secant is the same as 1 over cosine. So that's cosine to the negative 1, like so. Not inverse cosine, but like actually the exponent. And then yeah, and then the presence of these absolute values doesn't change the fact that you can still bring exponents outside of the logarithm. So if you take exponents outside of the logarithm, negative negative becomes plus, and so you can write this as this instead. If you want. Doesn't matter. Okay, so as a final example, let's take a look at this guy. So here we have a product of a sine and a cosine. So we have identities, trig identities that can deal with this situation, namely these ones right here. So product of sine and cosine, product of sine and sine, product of cosine and cosine. We have identities for that. In this case, it was a sine and a cosine. So let us take the formula for that, and then we're just going to plug that right into the integral and see what happens. Now, in this case, alpha and beta are like so, right? Is that the way it was written? Sine, cosine, yeah. So for us, alpha is 4x, beta is 5x. Okay, and then evaluating this dude should be straightforward. So the 1/2, we can go ahead and pull that out. So we have sine, so 4x minus 5x is negative x, plus sine, 4x plus 5x is 9x. Now, it's a little bit off-putting to have a negative inside of a sine. So at this point, recall that the sine function is odd. So sine x is an odd function, which means that it spits out negative signs. So sine of negative x is the same as negative sine x. So, because I don't like having that negative in there, let's just go ahead and pull it right out. So this is negative sine x plus sine 9x. Okay, and then let's just anti-differentiate this. So antiderivative of sine is minus cosine. So minus minus cosine becomes plus cosine. Antiderivative of this becomes minus 1/9 cosine 9x. And then finally, if you want, you can distribute that 1/2 through. I don't know why, but that makes me feel better. Like so. Okay, and that's all there is for that one. So yeah, kind of weird, kind of arbitrary. It's hard immediately to see why in the world we would be interested in integrals like this, but trust me, there is a reason for it. In the next section. Of course, you could just as easily ask in the next section, why do we care? But, at some point you have to just stop worrying about whether it's useful or not and just enjoy it for what it is. Then again, that's easy coming from me because I've chosen mathematics as a career. So, anyway. Okay, so that's all for this one.